pretty sure we've talked about this in a lot of different ways, so.
Can you give us the takeaways, what you want us to retain out of this, or?
Well, we'll see. I mean, you should know what the basic components are and what they do. You should know what a transistor is. You should know what a capacitor is. You should know what a diode is, what a resistor is. Kind of some things they're used for, right? I'm not going to get too deep. I'll throw a couple of different prepackaged components that are out there. But again, there's so many different things. The simpler thing to do is download a tech sheet and go from there. So primarily with digital technology, the goal of things is to automate processes. Okay, perform analysis, calculate formulas, and do something with this. Record data, do a whole bunch of different things, and to reduce the amount of human decision making that's rote, and a human doesn't need to really be involved in it. Right? The truth is, do you really need to know what the temperature is of something as a pilot? No, not really. In some cases, yes, it's helpful. But for the most part, no. What you need to know is when it's out of the appropriate range of operation. So I don't care what the oil pressure is, unless it starts to go out of range. But if it's not going out of range, whatever my normal operation is, I don't even want to see it. Okay, it's just distracting information. If I can automate that entirely to where I know when the oil pressure gets too low or too high, big red flags are going to come on and something's going to say, hey, you need to pay attention to this. Then great, that's one less thing I have to deal with. Now other information like airspeed, that's sort of a real-time feedback thing that you've got to have going constantly. Pilot needs to know that information as they're constantly adjusting. So if we can automate and reduce some things, then not a bad idea to start making use of this technology. We can also greatly increase accuracy as well as introduce data logging and a bunch of other things. So there are advantages to it. Obviously, the big downside was absolutely and effectively developed by Microsoft, called the Windows blue screen of death. You know, sometimes the digital stuff just stops working. Okay. Now, is it any more likely to stop working than mechanical gauge or anything else? I don't know. It's hard to say. I think there's more opportunities for something to break, but on the other hand, we can do a fair amount of stuff to make things redundant. So, and we've seen that. For example, in the world of turbine engines, we've gone to off-the-shelf electronics, subjected to very high levels of QA. But then they're so light, they're so small, just put 4 different computers on there in 4 different locations. And each computer is working in tandem with other computers to monitor each other. And if 3 of them decide one of them isn't behaving right, it's taken offline. And the other 3 take over. And on and on. Of course, turn on a big red light in the cockpit. So there are ways to achieve redundancy. So some things that are going to be important to all digital processing are these 4. You're always going to need a power source. Okay? Ship's power, generator, battery, whatever. They're going to need some power. They may not need a lot of power for the bulk of what they do. About the only place they may need some power is on the output side. When they turn something on and off, they may be controlling a fair amount of power. But the power that the digital system needs usually isn't very much. There will be inputs, information going in, data going into the controller that we pre-design. All the different variety of different inputs are going to be going in. There's going to be some kind of magic, little city in there with all kinds of decision makers making a bunch of pre-thought out decisions. And then based upon the input, the decision maker is then going to functionally do a bunch of outputs. Turn the igniter on, turn the igniter off, turn the fuel on, turn the fuel off, turn an ejector on, turn an ejector off. Okay, or somewhere in the middle. Maybe it's just a big red button that you push to start the engines, and it automatically does it. So okay, we're gonna hit the starter, start spinning things up at a certain value of both RPM and pressure ratios. We're gonna say, all right, kick the igniters on. Okay, the igniters are working. Got the appropriate amount of current coming through the igniter. So then I'm going to kick the fuel on. Okay, fuel's been on for X amount of time. I should see XYZ temperature rise. I'm getting the temperature rise. It's not going too high. Continue the start cycle, and on and on and on. And take it all the way through to the point that it then leaves, once it's done with its little scenario, says, okay, there you are at ground idle, ain't it grand? It's just one of a number of different ways of automating things. So the basic digital technology is actually a single pole, single throw switch, right? When it's open, the state of the circuit is 0 or low. When it's closed, the state of the circuit is high, or whatever voltage it's at. We could automate some of that with a bimetallic switch. That would be a very simple form. And let's say I use a heat-sensitive bimetallic switch that says, if the current gets too high, I'm going to open the circuit and go to a low state. Now we know that as a circuit breaker, right? But in fact, that's a digital device. It's making a decision based upon some amount of current to change the state of the circuit back to a low. Okay? Or I could do it to turn the light on, or a whole bunch of other things. Now, early on, we actually did make, we did all of this stuff instead of with integrated circuits and silicone and diodes, etc. We actually did do it with vacuum tubes. We can make, for example, a photosensitive vacuum tube that, as long as it was being hit by light, it would activate a relay that is normally closed. Okay, so when the vacuum tube activates the relay, it goes to open. But when the light goes away, the vacuum tube doesn't get much light, so it stops activating the relay. So the relay goes to its normally closed position, turning the light on. Now that wouldn't have been a very effective use of a vacuum tube. The problem with the vacuum tubes was they were large, very expensive to make, and used a ton of current compared to digital technology. But still, that's a legitimate decision maker. Now, one of the things I want to introduce here is the concept of high and low. I guess my two hickeys have disappeared. We say 0 or 1 for binary, or we say high and low, or we say VCC and VEE for reference ground and reference voltage. But we sort of have to be a little bit clear about what is high and what is low. At what point do you say the state has changed from high to low? And this is particularly true in an environment where I may be getting a variable voltage or not too stable power source voltage. So oftentimes I may want to have a decision-making voltage that's quite a bit lower than my source voltage. That way, if I get some variation in source voltage, my decision-making remains the same. That's why we have the 5-volt standard, 5 volt and 3.3 volt standard for most digital circuits. Because typically you're going to see 12-volt systems or 24 volt or higher. So as long as I keep all the decision-making down around 5 volts, and if that produces too much current, we'll kick it down to 3.3 volts and actually have even lower current ones. But ultimately, whatever my state is, we're going to say that's VEE, and up here we're going to say VCC. Could be 5 volts, could be whatever. So we'll pick a value. Let's say in this case it's 5 volts. What we're going to do is we're going to pick a couple of threshold values, and those be put out in the spec sheet for whatever the integrated circuit is. and we're gonna say this value, oh, I don't know, let's pick one, 3.3 volts, and here we'll say, maybe this is let's call it 3 volts, right here. So those two values are gonna be my threshold voltage, right? And the threshold voltage can work either way. What I can do is I can say if I've got a digital signal that's going to come down like this, and then it's going to come up like this, and come down like this. So at what point does this have to get below before we're going to call it a low? Having transitioned from high to low. We could say if it goes from something above 3.3 and gets below 2.3, we're going to say it's transitioned to low. And vice versa, we could say if it's below 2.3 and transitions above 3.3, it's going to be a switch to high. Or we could do it the other way and say there's a quasi no man's land in here, which says as long as it goes from something above 3.3 and passes to something below 2.3, we're going to say it's a transition. But if it just dips down to here and then goes back up, it wasn't a transition. Okay, so it stayed high the whole time. Now data is going to be, we're going to say data bit 1, data bit 2, data bit 3, data bit 4, data bit 5, high, low, 0. So in each case I could go, that's a 1, that's a 0, that's a 1. Let's say I did 2 heartbeats here. Now I got a 0 and a 0. Okay. If in fact I get stuck somewhere in here on that heartbeat, the computer, whatever is programming, could say, you know what, we got an error there. Something wasn't right. Something's wrong. So it might then, once it's done with that data packet being transmitted, it might kick back, retransmit. Something was wrong with that last packet. Okay. So part of this has to do with data validation as well. So when we say high and we say low, there are different strategies for determining what that actual decision is. All right. So we can automate some things with the standard, well, we talked about it, a PN junction, positive, negative, or diode junction. In this particular circuit, what did we do? So we said power switch is closed. And it looks like we've got a photosensitive device that's going to react, and it's going to change its resistance value if light hits it or light stops hitting. And when it does that, what it's going to do is it's going to let current conduct. Well, in this case, it looks like light hits it, right? When light hits it, it's going to cause current to start conducting. This being at 10K and that being at 1K, the positive is going to start exposing to the P of this NPN, and it'll turn the light on. Okay? If this goes dark, what's going to happen is the resistance is going to go way up. So now very little P is getting to here. So this is going to see 1K and 10K or 11K to N, and this might be, a mega ohm or something, whatever. It's pretty high because there's no light hitting it. So this NPN, this is going to go in, which will shut the transistor off. Okay, so that's just an example of a photosensitive diode. These aren't all that stable, but we do use them.
What's the nomenclature of the VCC and VEE?
We use that often because voltage could be anything. For integrated circuits, ground could be, EE is your ground reference for that part of the circuit. It could be -5, could be +5, could be whatever, and voltage could be, depends on the circuit, 5 volts, 32 volts, 82 volts. So a lot of times we just use those two references, VEE and VCC, or VGG for ground, one or the other, to indicate whatever the power source voltages are. And then you go over the spec sheet, and the spec sheets say VCC can be anything from. So it's call it a variable. So the vacuum tubes We use the term vacuum. Oftentimes they were not actually in a vacuum. They filled the little chamber up with an inert gas, which did a pretty good job, and they were at a probably at a much lower pressure. But putting a little bit of gas in there means that the pressure differential across that glass is a lot less, so it doesn't have to structurally be so darn strong. Okay, and as long as it's an inert gas, it won't get involved in any of the electrical reaction, or at least very limited amount. So other times they really were vacuum. So it turns out that what would happen is in this particular case, what did they do? They had so you had a cathode and an anode with a heater plate or a grid plate that if you heated the cathode up in the vacuum, it would start giving off a whole bunch of electrons, and it would work like a control switch, right? If I could heat this thing up and get this thing to behave like a control switch or like a transistor or like a relay. So that would mean while all I'm really doing is connecting this to here, I've got to have a whole bunch of other wires connected in, as well as a power supply to heat the grid up and do other elements, right? So very expensive. So some guy by the name of Russ, again, what was he drinking? You know, it's like Wankel. You ever seen the actual layout of a Wankel engine as the rotor hops around through the two orbits and drives the crankshaft of the knot? It's not really a crankshaft, but the output rotor around. I have no idea. That must have been one special cocktail napkin that they drew that puppy on. Because, but anyway, same thing here. This and by the way, this thing was huge. You can look it up online. It's a big, huge diode thing. They must have thought, well, this is kind of an interesting idea, but it'll never amount to nothing because it's so darn big. To make one is so big. Well, eventually, in the next 20-something years, you know, we had to take